I'm a postdoctoral research associate here at UNL, working at the College of Engineering. We know that we have more than 500,000 bridges in the US, but the American Road and Transportation Association reported that more than 1/3 of these bridges need serious repair or demolishing. As structural engineers, we need to assess the health of these structures. We need to find some cost-efficient damage detection systems.
As you can imagine, for any sensor technology that's deployed on a bridge out in the elements, these sensors deteriorate. This bridge was instrumented in 2018 as part of the Living Bridge project.
I'm working with a combination of virtual sensing and damage detection of these bridges so we can expand the coverage of the structural health monitoring system, a comprehensive framework that can use the estimated responses with the real responses that are measured using the sensors attached to the bridge to find if it's good to go or we need to do some serious repair or demolishing of the bridge.
What we were able to do is attach our smart data fabric to that existing integration, process the continuous strain measurements that are coming from that bridge, compute the root mean square at the edge itself. We came out a year ago, July 23rd, and we're still collecting data. We can see over a period of year how these different sensor values change over time.
This project is one of the series for structural health monitoring of bridges, where we're aiming to detect damages or anomalies on the bridge from sensing that is only mounted on the superstructure of the bridge.
We have applied some damage, but we're assuming that we don't know that the damage exists or the intensity of this damage. And we will apply transfer learning to transfer the knowledge that we gained from the previous truss into detecting and quantifying the damage into this bridge.
We were aiming to induce superstructure and substructure damages and detect that using sensors. We tested the bridge running a vehicle as a baseline or a healthy normal behavior.
This is a continuation of previous research. It's just the beginning of starting to get transfer learning working through different truss bridges or in the future different bridges across Nebraska or rural places.
Another damage we induced is around the piles of the bridge to develop a methodology that can detect the substructure damages from the sensors that mounted on the superstructure, which is crucial on the life of bridges as this is attributed to cause 60% of damages, for example, in the United States of the bridge infrastructure. We tested the bridge on the healthy cases and the damaged cases and compared the strain time history of the sensors and then applied machine learning dimensionality reductions method to detect the damage, locate the damage on the bridge, and differentiate the origin.
My name is John Helzer. I just finished my master's degree in mechanical engineering and applied mechanics at UNL. I came to this project about a year or so ago. We had a need for multi-copter-based bridge inspection. Ji Young was doing some work with camera-based algorithms that could identify problematic areas.
Is a very small GPU machine, just nano. This is very powerful. We are running deep learning model for this project, like object detection, which is drawing the bounding box for the rivets that we want to target. Low-level image features will like different colors or different shades.
We wanted a way to directly measure the bolts. Because I was designing a controller that was for a multi-copter with a suspended load, I tried to bring that controller to stabilize an end effector that could manually inspect the bridge. A multi-copter flies near the target bolt. The end effector shoots a rod at the target bolt, measures the resulting vibrations, and is able to characterize the bolt as either loose or tight.